Hi guys, welcome back to our second distant learning education schedule, and we will today work on the different testing procedures, how we generate new tests based on when we have composite hypothesis case. So let's continue with the new topic. But before that, let's summarize what we did in the most powerful test procedure. Here, remember, we use Neyman-Pearson lemma. In the most powerful test, we are conducting our testing procedure as reject A0 if simple likelihood ratio, which is L theta 0 over L theta 1 less than or equal to K. And after that, basically, this procedure turns out to be the case that we have a sufficient statistic y less than or equal to C, or y greater than or equal to C case. And this y is usually a sufficient statistic for the unknown parameter theta. Here we assume that our null hypothesis states that theta equals to theta 0, versus we have the alternative theta equals theta 1. Okay, so we ended up with one of the testing procedure where y less than or equal to C or y greater than or equal to C. Then we have to find the value of C. And in that, we are using the known information, which is the size of the test, probability of rejecting null hypothesis, reject 80, when 80 is true case. Okay, so here we are writing our simple likelihood ratio less than or equal to K given theta equals theta 0. Okay, and then in terms of y, we will see that we can have y less than or equal to C depending on the value of theta 0 and theta 1 equal theta 0, or we can have alpha equals probability that y greater than or equal to C given that theta equal theta 0. So in this case, to be able to find the value of C, you have to use the PDF of y. Okay, so this is important here. If we have a just single random variable, then our simple likelihood ratio turns out to be a PDF under the null hypothesis over the PDF under the alternative hypothesis. In that case, your testing procedure will only depend on x. Okay, so not a function of sample random variables, but assuming that we have a sample of size n, y is a function of sample random variables like summation xi or x bar or whatever, or sample standard deviation kind of thing, and then using the distribution of y, we find the value of C using the probability definition of type 1 error. Okay, so this was the testing procedure for the most powerful test, and after finding the value of C, we can write the most powerful test of size alpha easily. But then, let's say this is a simple hypothesis case where our simple hypothesis defined using this. Let's consider a different type of hypothesis. Okay, so here let me write the name of the procedure here, uniformly most powerful tests, which are known as UMPT. Okay, so in this case, we have a random variable x where the PDF is known and theta is in the parameter space, and here we assume that our alternative hypothesis is in the composite hypothesis type. So let's say null hypothesis equals theta 0, versus we have the alternative where theta less than theta 0 or we can define our alternative hypothesis as theta greater than theta 0. Okay, so we have a composite hypothesis. So we have infinitely many numbers of theta which is less than theta 0 or greater than theta 0 in the alternative hypothesis actually. Okay, so here our testing procedure is if a test is the most powerful against every possible value in a composite alternative hypothesis, then it will be called a uniformly most powerful test. Okay, so let's say we have a null hypothesis and here theta equals theta 0, and let's say we defined our alternative hypothesis in this way. And then every possible value, so we have infinitely number. So here if we define the null space here, so we only have theta 0. Okay, and here if we define the parameter space for the alternative, so it is defined by theta greater than theta 0. Okay, so we have infinitely many numbers here, all of them greater than theta 0. So what is the testing procedure here? So in the most powerful test we have only one value of theta in the alternative hypothesis, but right now we have infinitely many numbers here which are greater than theta 0. So for each possible value in the alternative value of the parameter in the specified under the alternative hypothesis, so we have a most powerful test, so we will derive that. So because of that, the name is uniformly most powerful test. So we are using the same most powerful test procedure, but for every possible value that is defined under the alternative hypothesis. So it is uniformly most powerful test. So we have two options actually. In one option here, we can say that actually just select one particular value of theta under the null hypothesis and show that it does not depend on a specific alternative value, and then develop the test. But it is it's not a efficient way to do that. But let me write this approach. But we will not use this approach. A uniformly most powerful test often exists in the case of one-sided alternative. Let me say composite hypothesis. Actually one-sided, let me erase this one also, alternative I have to say, hypothesis, and one way to develop the most powerful test, uniformly most powerful test in this case, is to derive the Neyman-Pearson lemma. Remember, we define our most powerful test based on the Neyman-Pearson lemma for a particular value of theta, let's say theta 1 is in the alternative space, and then show that the test does not depend on that specific value of theta 1, does not depend on the specific alternative value. Okay, so this is one way to do it. For example, we can consider a normal case, and here when sigma square is known case, and then remember we concluded that our most powerful test here for specific value of mu 1, our testing procedure was reject H0 if x bar greater than mu 0 plus z sub alpha sigma over square root of n. This was our most powerful testing procedure. So here basically if you look at the testing procedure, there is no mu 1 term. Okay, so no matter, so mu 1 only appears in the power of, when we calculate the power, no matter what mu 1 is in H1. So if we show that for a uniform most powerful test, our testing procedure does not depend on mu 1, this case, so then we have the most powerful test of alpha. But it is not an easy way or efficient way to do that. Another way is finding some statistic. Okay, so another way of finding the UMPT, uniformly most powerful test, is the use of some statistic which is known as the monotone likelihood ratio. Is the use of the monotone likelihood ratio. So this is the easiest way to deal with the composite alternative hypothesis case. Okay, so how we can do that? So we are writing simple likelihood ratio again. Although we don't have the value of theta 1, we assume that any parameter value in the parameter space of the alternative hypothesis can be any theta 1 value. Okay, so we are writing it as L theta 0 over L theta 1. Although it's not specified like in the simple hypothesis. Okay, and if we show that this simple likelihood ratio depends on our sample random variables x1 through xn only through some statistic y, which is a function of sample random variables, and if we show that this simple likelihood ratio is an increasing function of y for every given, this condition is important, theta 0 greater than theta 1. Whatever the direction of the alternative hypothesis, here in this procedure we are not looking at our hypothesis. So this is the regular definition actually. So first of all we have to find the simple likelihood ratio. Although we don't have any specific value for theta 1, symbolically we find L theta 0 over L theta 1, and then we have to show that this statistic depends on the sample random variables only through some function of y, and we have to show that L, the simple likelihood ratio, is an increasing function of y for every given theta 0 greater than theta 1. Okay, so this is important. So here you don't look at the direction of the alternative hypothesis. Whatever the direction of the alternative hypothesis, you have to use this rule to find the monotone likelihood ratio statistic. Okay, then we say that we have a monotone likelihood ratio. We use MLR notation for that in the statistic Y. Okay, so our L, simple likelihood ratio, is a function of sample random variables only through y, and we have theta 0 and theta 1 values in the simple likelihood ratio. And if it is an increasing function, if L is an increasing function of y, then y is our monotone likelihood ratio statistic. Okay, and reversely, if L is a decreasing function, okay, so if L, let me write it nicely, if L is a decreasing function of y, then decreasing function of y for every given theta 0 greater than theta 1, then our monotone likelihood ratio statistic is minus y. Okay, so this is how we define our monotone likelihood ratio statistic, and then we can define our test. So we will see how, but let's focus on this likelihood ratio again. And then here, previously we showed that likelihood ratio is a function of sufficient statistic, then we have the same situation here. If a sufficient statistic for theta exists, then y is either the sufficient statistic or a function of that specific sufficient statistic for theta. Okay, so it also depends on sufficient statistic or a function of sufficient statistic. So when we have a monotone likelihood ratio statistic y, it's also a sufficient statistic for theta. But the reverse is not correct. So here we are not starting with finding the sufficient statistic. Okay, so we are starting with the monotone likelihood ratio statistic, and we know that it's a sufficient statistic, but we cannot say the reverse. If y is a sufficient statistic, it's not always the monotone likelihood ratio statistic. Okay, so be careful about that. If we don't have a monotone increasing or monotone decreasing function, basically in those cases we don't have monotone likelihood ratio statistic. So if L is not an increasing or is a monotone, let's say is not a monotone function of sample random variables, then monotone likelihood ratio statistic does not exist. Okay, so in this case we don't have any monotone likelihood ratio. And then, so what is the testing procedure? So let's give this with a theorem. Okay, if a joint PDF f of x1 to xn given theta has a monotone likelihood ratio and the statistic y, which is a function of sample random variables, then a uniformly most powerful test of size alpha for testing theta less than or equal to theta 0 versus h1 theta greater than theta 0 is to reject h0 if y greater than or equal to, sorry, I have to write this lowercase y, greater than or equal to c, where alpha equals the probability that y greater than or equal to c given that theta equal theta 0, under the case that where the null hypothesis is true. Okay, so here when we try to find the monotone likelihood ratio statistic, we are not looking at the direction of the test, but in the uniformly most powerful test, after finding the monotone likelihood ratio test, so in that case, after finding the monotone likelihood ratio, look at the direction of the test. Okay, so here our test is theta 1 greater than theta 0, so our testing procedure is monotone likelihood ratio greater than or equal to c. So we are using the same direction, put an equality sign here. Okay, so basically direction based on the direction of the alternative hypothesis. Okay, so if we have the test that a0 where theta greater than or equal to theta 0 versus h1 theta less than theta 0, here after defining our y, rejection procedure will be reject a0 if, now we have y, and look at the direction of the alternative less than or equal to c. Okay, so we are using the same directions. Okay, so in the direction, in the definition or derivation of monotone likelihood ratio statistic, we are using the case that L is a decreasing or increasing function of L. So L depends on Y under the condition that theta 0 greater than theta 1 case. Okay, so this is always the case, whatever the alternative hypothesis is. Okay, so this is important, so you have to be careful about the derivations. And again, after defining the direction of the test using the type 1 error probability, we define the value of c. Again, these procedures are always the same, so finding the c using alpha, we can derive that. Okay, so let's solve some questions. So uniform question, I will solve the uniform question later. So okay, so let's derive the exponential. It's kind of easier. Okay, so this is the testing procedure. Okay, find y depending on the simple likelihood ratio. Okay, and then show that it is monotonically increasing or decreasing function of y, and under the condition that theta 0 greater than theta 1. And let's say if it is an increasing function of L is an increasing function of y under the condition that theta 0 greater than theta 1, y is the monotone likelihood ratio statistic. But if L is a decreasing function of y, again under the condition that theta 0 greater than theta 1, then monotone likelihood ratio statistic is minus y. Okay, after defining the monotone likelihood ratio statistic, then you go through the direction of the test or rejection region of the testing procedure. Okay, so let's solve some examples. So let's say we have an exponentially distributed random variable. Okay, our parameter space is the positive random variables, and here let's assume that we have a random sample of size n. And our hypothesis is given that theta less than or equal to theta 0. You can also define as theta equal to theta 0. You will end up with the same result actually. Okay, so it doesn't matter to use these two. Important thing is the direction of the alternative. Okay, so construct uniformly most powerful tests of size alpha. Okay, finding type 2 error probability or finding the power, so all the same actually, it's not different whether it's most powerful test or uniformly most powerful test, so you will use the same testing procedure. Okay, so what is our first step? Is finding the simple likelihood ratio. Okay, so let's do that. But we are finding the simple likelihood ratio under the condition that theta 0 greater than theta 1. So at this point I am not looking at the direction of the test, so I forgot about the test right now. Okay, so just find the simple likelihood ratio and consider that theta 0 greater than theta 1. Okay, so find the ratio, and since we have a random sample of size and find the likelihood ratio, theta 0 to the n e to the minus summation xi over theta 0 divided by 1 over theta 1 and e to the minus summation xi over theta 1. Okay, and then write this as theta 1 over theta 0 to the n and e to the minus summation xi 1 minus theta 0, 1 minus theta 1. Okay, now use the condition that theta 0 greater than theta 1. So this part is positive, although it's between 0 and 1, so it's positive. And we have to focus on this part. Okay, so this part, and then we have to show that L is a decreasing or increasing function of theta. Okay, so here theta 0 is greater than theta 1, but we have also the minus sign here. Okay, so this means that basically when theta 0, when summation xi increases, this simple likelihood ratio increases, right? So when summation xi increases, L also increases. So this means that basically summation xi is the monotone, L is a monotone increasing function of summation xi. I'm sorry. Okay, so here we have to say that our simple likelihood ratio depends on the sample random variables only through, because we only have summation xi here, only through summation xi, and it is a non-decreasing function of summation xi for theta 0 greater than theta 1 case. This means that our monotone likelihood ratio statistic is summation xi let's say it's y. Okay, so we found our monotone likelihood ratio statistic. Then, in the construction of our uniformly most powerful test, then our testing procedure is reject H0 if our summation xi. So at this point, go to the hypothesis, and then here see. Okay, so here look at the direction of the alternative. It is theta greater than theta 0. So do the same thing here. Put an equality sign. So this will be our testing procedure. Now our job is to find this C. Okay. So let's find C. How we are finding C? Using the known information again. So what is our known information? Okay, so we know theta 0, we only know theta 0. We know the sample size. But what other thing we know is alpha. Okay, so we are using that. So it is given to us. So using the definition of alpha here, this is the probability that, again, use the definition of probability of type 2 error, which is reject A0 when A0 is true, right? Okay, so what is the rejection region? Here our statistic summation xi greater than or equal to c, given that theta equals theta 0. Okay, so to be able to find c, we need the PDF of summation xi, right? And as you can guess, we start with exponential. What we will end up is gamma and then chi-square actually. Okay, so x distributed as exponential with theta. Then we know that summation xi for a random sample, each sample random variable independent from each other, then they distributed as gamma with parameters and shape parameter and scale parameter theta. Okay, so this is very general and it's not user friendly, and we know that there is a close relationship between gamma and chi-square, and we know that chi-square has a table value. Then if we have a chi-square table, we can easily define the values, but for different sample sizes and different values of theta, it's not easy to define this testing procedure. Okay, so what we are doing in gamma, converting gamma to another gamma is very easy, and you know that for gamma to be able to distribute as chi-square, we have to change this theta parameter to 2. So, and this is a scale parameter, and we know that if we multiply or divide by some constant, it only affects the scale parameter, this parameter. So if we multiply our statistic by 2, okay, then this theta also multiply with 2, and if we want to get rid of theta, what we have to do is divide it by theta. Okay, so our statistic is that one. So if we do that, we have gamma n and 2. Okay, so which is the definition of chi-square distribution with 2 n degrees of freedom? We are just multiplying scale and shape parameters here. Okay, so we know now the distribution of our statistic. So let's turn this to a chi-square random variable xi. So here we assume that our true theta is theta 0, right? It's given. So do the same thing for the other side of the inequality, and here theta equal theta 0. Okay, so we already showed that we have a chi-square random variable with 2n degrees of freedom, 2c over theta 0. So now we still couldn't find the value of c. Okay, so this is alpha. Alpha is like 5%, 10%. It's very small number. So if we have a chi-square distributed random variable, the shape is something like that, and then we assume that our chi-square random variable is greater than some value 2c over theta 0. It has this small probability, so it's in the upper tail, right? This probability is alpha, 5%, 10%, and this point is 2c over theta 0. And we know that from the chi-square table or distribution, this is chi-square 2n with alpha degrees of freedom. We are using upper tail probability here. Okay, so now from here we can find the value of C as theta 0 chi-square 2n alpha over 2. Okay, so now we found our C. So what is our UMPT of size alpha is to reject A0 if summation xi I from 1 to n is greater than or equal to RC. What is that? Theta 0 chi-square 2 and alpha over 2. So this is our test. So after finding our test, so RC is now defined by the test. It does not depend on theta 1 or any value in the alternative hypothesis. So this is our uniformly most powerful test. After that, we can calculate the power of the test. So it's exactly the same as the example that I saw for the most powerful test case. Okay. Okay, so let's give a break right now. I will continue with other examples.